Okay, this is my solution for the problem that we did on Monday of week 2. This is a pretty complicated problem, but it's good practice to see all of the different things you can ask about a simple setup like a ball being tossed off a cliff. So if there's an initial velocity, let's just call it v, and it's at some angle theta with respect to the horizontal, if you know the height of the cliff, that's pretty much all you need to know. So let's start, before we even look at the questions, let's start by writing down some things that we already know. And the first thing I'm going to do is I'm going to define that upward is the positive y direction, and to the right is the positive x direction. Now I realize that's not the choice we made in class, but I really want to illustrate here that it doesn't matter what choice you make. You always get the same answer as long as you're being consistent. So the first thing we know is the velocity, and we know that the velocity in the x direction is v cosine theta, and the velocity in the y direction is v sine theta. And I'm going to check, yes indeed they are both in the positive direction, positive to the right and positive up. And I just want to remind you how I know that is that I have a triangle here with hypotenuse v, and the two vectors that sum to make v are the components theta, if that angle's theta, so cosine theta and sine theta. If I picked this to be the angle, okay, then it would have been different. So if this is phi, this would have been v cosine phi and v sine phi. Okay, but we'll stick with the cosine, because that's how it was given. Okay, so let's see, what else do I know? I know x naught is 0 and y naught is 0. Let's see. I don't know x final. Oh, these were knots. And I don't know anything about the final speed, I guess. I do know that y final is equal to h. Be careful, though. We said it's positive upward, so when it lands, that's a negative h. Okay. Let's see. What else do we know? Oh, we know the acceleration. We know that the acceleration in the y direction is equal to g, and it's downward, which is negative in this coordinate system. Now the acceleration in the x direction is 0, which means that the final velocity in the x direction has to be what it started out with, so v cosine theta. So now that I've set this up, now that I have a full and complete bookkeeping, now I can start to ask the questions that I want to ask. Okay, so here's the first question. The first question is, when does the ball land? And, you know, the first thing that occurs to me is that I'm going to use the y direction. The x isn't going to be very much help, because if it weren't for gravity, it would never land. So I'll say that y is equal to y naught plus v y naught t plus 1/2 ay t squared. So I know that the final is minus h when it lands. The initial was 0. The initial velocity is v cosine theta times time, and now it's 1/2, and the acceleration is g. It's minus, so I'll put the minus up front, t squared. And here I'm going to make a pause, and I'm not happy. I'm not happy because I hate solving quadratics. Now, that doesn't mean it can't be done, but I'm just showing you how I would solve this problem. And I would probably say, you know, I think it really is worth it trying to find some intermediary thing. So what might I find? Let's see. You know what I would probably do? I would probably try and figure out what the final y velocity of it was without worrying about the time. So instead, I'm going to ask, what is the final after the fall? And I ask that because, well, first of all, this is my favorite kinematic equation. I don't really know why. V y naught squared 2ay y minus y naught. Because see, I know everything else here. So I know that vy squared minus v sine theta, oh, which makes me realize, actually, just looking up here, this was supposed to be sine. There we go. Sine theta squared is equal to 2 minus g, so I put the g out front, and the y final is minus h, and the y initial is equal to 0. Okay, so now what am I going to do? Well, I guess I'm going to solve. So vy is equal to v sine theta squared. So that's a plus sign plus 2gh. And I'll take the square root of the whole thing, and that's a velocity. Cool. So I'm going to pause now and plug that into my calculator. Okay, I'm back. I did plug that into my calculator with the values that were given, and I got that it was 60.7 meters per second. But I have to be a little bit careful, right? Because as it's heading downward, that means that its velocity in the y direction is negative. You know, when you take the square root, it could be positive or negative, and it turns out that it's going to be negative when it's heading downward. So you might think this is a lot of extra work, but in fact it makes it pretty easy now to figure out when does the ball land, because now I can simply ask if v initial is v sine theta and v final is equal to minus 60.7, what is the time? And that's actually pretty easy. So here we go. We get that v initial, let's see, v final is equal to v initial plus, in the y direction, sorry, plus ay times t. So I get that the time is equal to the final minus the initial divided by the acceleration. So I started with a v sine theta, and I ended with a 60.7 meters per second, and my acceleration is minus 10. And I notice actually this is going to work out okay because all of these minus signs cancel. So I can multiply through by minus 1 on the top and the bottom and easily get an answer. Okay, so once again, I'll plug this into my calculator. And I'm back, and I plugged that into my calculator, and I got 9.8 seconds. So maybe that seemed like a lot of work, but usually I find that whatever way sort of makes intuitive sense to me, it's okay to proceed as long as you're careful with what you were finally asked. And in a problem like this, it might turn out to be something I need later on. Okay, so here's the next question. The next question is, where does it land? What is this asking? This is asking what x final is. Well, that's a pretty simple equation because there's only one kinematic equation in the horizontal direction. It's x equals x naught plus vx naught t. So I get that the final x is equal to the initial 0 plus, now my speed is v cosine theta, and I'm going to multiply times the time, 9.8 seconds. And when I do that problem, I get that it comes out to 520 meters. Wow, that's a long ways. Okay, that was pretty easy. Let's see, how high does the ball go? Let's see, how do I want to solve that one? Oh, I think I know what I want to do with that one. I think what I'm going to do is I'm going to say where, this is what this means, where does the y velocity go to 0? Because that's when it turns around. So let's see, I need a kinematic equation that doesn't have time in it. So I'll try this one. Vy squared minus Vy naught squared equals 2ay times y minus y naught. So let's see, I have a 0 minus V sine theta squared is equal to a 2 and a minus g, which is going to be 10. And then the y, I don't know, and the y naught is 0. So when I multiply through, I get Vy, so let's see, y is equal to V sine theta squared all over 2g. And when I do that, I find that the total y that it goes before it turns around is 69 meters. Okay. Wow, I'm on a roll now. So the last thing that it was asked, I can't think of what else it might ask, although you could ask a lot of things now, right? You could say, how long does that take, and so on and so on. But the last piece was, what about speed and velocity before it hits the ground? And as we said, the velocity, the final velocity, is going to be equal to its x velocity, I hat, plus the y velocity, j hat. So what do we know about these things? Well, actually the x velocity has to be exactly what it started with. That's the whole point of the projectile motion. And you know what's interesting? We actually already have the y velocity. Yeah, I'm going to come over here and make a star next to that. See, it did pan out for me. So what I had left is the minus 60.7. In fact, I think I'll just write it symbolically here. So that's plus Vy was the square root of V sine theta squared plus 2gh. And that's the j hat component. So how do I find the total speed? This is the vector v, and the magnitude is just the speed. And so if I take the x component squared and the y component squared and I take the square root, I can find what the total magnitude of that vector is. And when I do that, I find that it's 80.7 meters per second. And we're done. Ta-da!